Plan projection. We'll get to what those words mean in a second. Do you remember the first lecture or two when I showed you what the picture plane is? I told you how really you can solve some of the most difficult perspective problems. You can solve them if you understand the concept of the picture plane being a window that you hold perpendicular to your line of sight, which means wherever you move, it's got to be parallel to your face plane, perpendicular to your line of sight. You can't start tilting it around. And that if you think of the picture plane as a window like that you can move closer or further away, and then you would draw with a grease pencil lines of hold that thing still, draw lines on that window that represent things out there. That's what perspective is about. And I showed you how a pencil or something of equal length, if they go back in space, how they intersect the picture plane at different points and make something look smaller. It's very important that that lecture was given before this one, because that's what this plan projection is about. It's about the picture plane. Now here's why we spend a session on this. Some of you who already know what plan projection is feel like this is something that architectural illustrators and industrial engineers need to know, but students of fine art and even illustration, do they really need to know how to do a plan projection? The answer is no. You don't really need to know how to do a plan projection. But in my experience as an illustrator, and you know what I do, you've seen the technical stuff that I get involved in. In my career, I've only had to do this 3 or 4 times. But I'll tell you, those 3 or 4 times, they say it saved my neck. I couldn't have done without it. If you are going to be an architectural illustrator or whatever, you'll really need this. But here's a time when most people would need it. We've had some times in here where we were solving problems where you really needed an accurate square in perspective, didn't we? I mean, it had to be a square. It couldn't be just like a square. And when it's in perspective, when it's not in perspective, you can eyeball it and get real close. I'm just a little bit off there for a perfect square. But if you were 10% off on that, which I was about 5%, if you were 10% off, you'd be able to see it. But when it's in perspective, it might not be a real square. I might be 20% off and not see it. But sometimes it's got to be a perfect square if you're going to be making it go down further, up higher, off to the side, because the distortions will make it evident. There are times when you need a perfect square, not just for that reason, but also remember when we were doing hinges and trying to place ellipses? And you really have to have a true square that a perfect circle fits in perspective so that it will be correct. And some of you have run into this problem where you're trying to do how do you know it's a perfect square in perspective? Well, there are different ways to know. Watson, in his book on creative perspective, says that the way you learn whether it's a perfect square in perspective is you draw cubes by the hundreds. Until when you can tell when that's 10% off, you draw this in perspective over and over and over by eyeball onto paper. And when you've done it a few hundred times, you can look at that and say, oh, it's 2, whatever. You'll know because you've got it in your brain. Of course, that's the best way, because that way it's in you. And you don't need any outside reference because you've got on your brain that blueprint. Most people won't do that, though. There is another way. You can buy one of these books or grids called Perspective Made Easy, or the No Pain Perspective Method. And what do? They will give you grids that will be things like squares or buildings or some kind of grid in perspective, and they'll say, just use this. And that works. But it's got one big problem, and that is it might not be in the position you wanted it to be for your composition, for your idea. And so you'll conform it to one of these painless perspective grids, and you'll get it correct, but it will not be what you intended it to be. I don't like those things. I like either what Watson does or what Marshall says, which is, as a last resort, if you absolutely have to have something that you know what it looks like in this position, out of perspective, and you need to tilt it in space, and you've got to get it right, as a last resort, you go to plan projection. It will work, but it's a tough trick, and I'll show you how to do it. Now, if we need to get a square absolutely accurate in perspective, that should be pretty easy, considering that architectural engineers, that industrial designers have a blueprint of what? Of a house, that is a floor plan and an elevation, front or side, or of a telephone, or of a calculator. These are blueprints. And they can take those blueprints and do a perfectly accurate three-dimensional perspective drawing. It will be perfectly accurate, without photographs, and they can render it any way they want. They can make up their own light and light it just like they want. And if they want to, they can do it more wide angle or more telephoto, in effect, by simply moving a dot on that board. They do this with computers now, but we're going to do it the old way so you understand the theory that goes behind what they're doing with the computer. Okay. The word plan, what does it mean when we're talking about it this way? What is a plan? Go ahead. It's a top view looking down from a helicopter. So when you say these are the floor plans of this house, you look at those floor plans because you want to know where you're going to put your flat files and your drawing board and your washing machines. It's just the floor plan. It doesn't tell you anything about the height of things, just the floor layout. So the plan is a non-perspective helicopter view looking down. Think of floor plans to help you if this is new to you. There's something different from a plan, though, that you'll need to do this elevation, or to do this projection business, and it's called elevation. What is an elevation? What? A side view or a what? An elevation can also be a front view. But elevation has to do with what that word means. It's the height of things. It's a how high does this object elevate off the ground. So it's a side or front view. Now, cube, which is the first problem we'll solve. What does the plan of a cube look like? What does the elevation of a cube look like? Exactly the same, whether it's side or front. You've got the exact same plan and elevation. However, if we're using this thing, and this is the World Trade Center or whatever it is, what does the plan look like? And what does the elevation look like? That's right. The elevation will be something like that. Important information, because from those two things you'll see you can deduce. We're going to use this one at the risk of it being confusing, that there's no difference between the plan and the elevation. But I'm going to do this more than once. And the second time I do it, I'll use one that has a different elevation than plan. Okay, so we've defined plan and elevation. Now we've got to define projection. Projection means getting it from the blueprints into a three-dimensional perspective drawing. There are two steps.
Would that elevation be any height?
Yeah, yeah. And also, here's another thing. What if the plan looks like this? The elevation might look like this. Can you see that? Oh, well, that's further away from us than that. Or the elevation might look like this, right? And that's closer to us than that. Okay? And this is where you have to think in these three categories: top view, front view, side view. And that will give you the clues as to how something is shaped. Okay, two steps. Don't try to copy it because it's in the books and you need to see this. If you're going to do a plan projection, let me work over here. I need as much vertical space as I can possibly get. You need to have a plan to project. you're going to have to put that plan on there in a position. But before you do that, what might that line be for a plan projection? What might that represent tilted onto edge? A picture plane. Remember, we're in a helicopter looking down on the edge of a window, and we're going to have somebody here looking through that window at what? Let us make it a square. A perfect square. I'm going to measure it to make sure that it's perfect. Yep, close enough. A little convergence there that ought not to be. But I've also got to make this thick enough lines to where it comes through. Looking down on cube, or on at least on square, that we want to turn into perfect perspective. Now, who's looking at the square? That's the next important thing. You've got a picture plane that you're looking through. You can see on the other side that this corner is touching. You'll see why that's important in a moment. It doesn't have to, but it makes things a little simpler. Now we've got to put somebody looking at it. If we put them up here, what happens to what they see? Wide angle effect. If we put them way down here, what do they get? It flattens it out, less perspective. We talked about that, right? The further you get away, the more the vanishing points go out. The closer you get up, the more the vanishing points come in and give a wide angle effect. Well, we're going to need this area down here, so I'm going to put this character right about here. That's a person. You're looking down on their head, person with one eye, looking through window at this big square. Okay, now let's imagine you're looking through this window. What are the 4 important points? The corners are the important points if you're going to connect dots. So imagine that each corner sends a little beam of light, which it does, sends a little beam of light to this character. You want to track on a straight line that beam of light from this corner, from that corner, and from that back corner there, and of course there will be one from that corner. Now we use that straight line to find that beam of light that goes from those corners, but of course the beam is not what's important. What is important is the point at which the beam touches what? The picture plane, because this is what our character is going to see, is these dots, which will be lines. We're looking down on it, so there's no perspective to this. Those are the crucial points. Now, what I'm going to do, this is important that you watch this. We're looking down on picture plane. Here's what we're going to do in a moment. We're going to go like that and see what this character's seeing. Okay? We're going to pull it out of perspective. But when I do that, let me just go ahead and do it right now to show what kind of problem I'm going to run into. When I pull it down, these lines, let's go ahead and get rid of this, these lines that we use to find these points. Get rid of our character. No, we can't get rid of our character yet. You'll see why. Those are going to go perfectly vertical as I tilt that thing down. But there's another thing I've got to find before I tilt it down. I've got to find where the vanishing points for these lines that are going away from this character in space, I've got to find where those vanishing points will be on the picture plane. And there is a quick way to do it. This is where our character was. Parallel lines look like they meet at a vanishing point. So we've got to have another line parallel to that, and it should be a line coming from our character, going off to the same way that's going, parallel with that line. It's going to hit there. Now we've got to have one that's parallel to these lines to find that vanishing point. How do you check whether it's right? This should be a 90-degree angle, because it's like this one. Okay, now I'm going to do that again later if I lost you. I know that's a point where people get lost. I needed to find where the vanishing points were going to be on this. So I needed a line parallel to that. Oops, hits it there. There'll be a vanishing point there that when I tip this down, like so, is going to be on that line. And when I tip that down like so, that one's going to come down there. Remember, your cone of vision is 60 degrees. That's a 90-degree angle. Your cone of vision is going to be more like this, so you won't see those vanishing points in your line of sight. Now, I'm going to erase these lines that I used to find those lines, and let's thicken up these points I made. Are you with me so far? That's a pretty important point right there, right? That's going to be the front corner of our square in space. So I've got to determine something, which I've always got to determine when I've got a picture plane. I've got to determine where my eye level is. If my eye level is right there, where are my vanishing points? One of them's right there, and one of them's right there, which means I can then get rid of these lines I used to find my vanishing points. I've taken those lines, those points for the vanishing points. I've gone like that. I found where they are on the horizon line, which I arbitrarily put there, so I don't care about that. I found my vanishing points, which means if this is the front corner, I could put it anywhere. Let's say I want to put it right there. Now, can you see what I'm going to do? Actually, that's a little bit too radical a perspective. Let's try it right there. I'm going to connect that line. I'm doing this line in perspective. It's going to go back there. Look at where it hit. It hit on the point that represents that corner. See how I'm going to do the other line? This line, which means it's going to go back to that vanishing point, and it's going to hit right there, which represents that corner projected down there. Now it's a matter of connecting the dots. I want to find where that one is. It's on this line, which means if I go back there, it's going to hit at that point, and that's going to connect over to there. Now what I've got, if I was doing this with straight edges perfectly, would be a perfect square in perspective. I projected it from flat, found where the lines went to that viewer, erased all of that work that I needed to find that, and then went like this. All those vertical lines came down, but this doesn't tell me anything about, what? It doesn't tell me anything about the height. We'll say it's a cube, but remember, it could be a pillar. So how are we going to find the height? We've got the plan projected now, the floor plan. How are we going to find the height? Well, remember, we have to work with a line that's not in perspective, that's not tipped away. And there's only one line that would be high up there that wouldn't be in perspective, and it would be the front corner if this is a cube, which would be this line that we're going to find the height on. What will the height be? It's got to be, let's find those marks. All right, that's non-perspective. Run that along there, run that along there, and in other words, I'm putting the elevation of that cube, putting that elevation here and running the lines non-foreshortened, like so, and then you see what I'm going to do? Just connect the dots again. Connect the dots off to these vanishing points, and you will have both the height, the elevation and the plan projected. It's a perfect cube. If it had not been a cube, if we had decided that this thing was that high, it was a block like so, we would have just run this over to the front corner, the non-foreshortened line. I lost my vanishing point. There it is. And we would have run lines like this. And that would have been accurate. Did you follow that? You ready to see it again? Now there's variations on this. You can actually put the plan down here and have the viewer and project lines back and make them hit there. You can, one of the things you can do, and Watson does it in the book for clarity's sake, is that he keeps all this stuff that he used with the viewer keeps that there, and then runs that picture plane down further, and then builds the three-dimensional model down here so that you can see the scaffolding that he used to find those points, and then you can see the perspective drawing. I had to erase it because I didn't want to do this down here. But you'll find in different books there's different variations on this. And of course, when you're projecting house plans, which there's a not so complex projection of house plans right here, instead of having 4 points, you could have 40. It could have a lot of different points, crucial points to work with. Okay, I'm going to do one. Go ahead.
When you're working with, let's say if it was finished.
Yeah, you can project a cylinder. And there's more than one way. One thing is to project the middle line, the center line of the cylinder. Another way is to fit it in a box, as you said, or just find a few crucial points. Right? If you can find that point and that point and that point and that point, you know, you're on your way. You've got 8 points there that are going to help you. You can also decide exactly what tilt this is at. And there is a way. In fact, which book is it that does this? Grumbacher, I think, or I think it's Grumbacher has a book on perspective where he shows you how to do that. That's getting even more. It's going to get more complex that way, and I'm not going to go into it. I'm not prepared to go into it. If I came to a problem where I was running like that, I'd go to the books and figure it out and then do it. One of the things this helps you with, even if you can't do this, it's good to understand it because it helps you think in terms of 3 dimensions as opposed to 2 or 4 or 9. Things have a top and a side and a front. And at the bottom is simply the same as the top in the sense of if it's cubed up. The back is the same as the front. The other side is the same as the side. You're thinking in terms of right-angled blocks have 3 dimensions and variations on them. And if you can think this way, you can start to look at plans and elevations, and you can start to see, okay, I see what that would look like. Just like you can design your cartoon character from the front, the side, and the top. And you don't have to do plan projections. You can start to do freehand drawing and know how to conform that shape so that it will be consistent in any position. Okay, let's try it again. This time, let's do a couple shapes. Let's do a rectangle like so. And let's do a square like so. And maybe we should make this a little more, well, I'm going to end up with too many lines. Let's do a square in 1 point. I might do this a 3rd time if you all desire it, but I might not if you don't. Depends on what your energy level is like. Let's do a square in 1 point. Got to choose where we're going to put our viewer. Let's put our viewer right here. Can you all see that? Viewer looks at picture plane and sees little points of light. How do we find them? We simply run, and they've got to be perfectly straight lines. You're wise to use your straight edge. Well, you have to use your straight edge if you're doing this. A little awkward on a board, but there's going to be that back corner that you care about. There's going to be this front corner that you care about. It's touching that glass. There's going to be this one, and there's going to be that one back there. And if you can get all these lines perfectly straight, perfectly accurate, you only care about the point that they cut through that picture plane. The rest of it, you can get rid of. Likewise with this one over here, you care about that beam of light that goes there from that far corner. Since these are boxes with 4 corners, you're going to have 4 points you care about. You don't need to run one for that one, but you do need to run one for that one. You care about these points. Okay, once you've got those points, what else have you got to get before you tip this down? What are you going to need? What? Vanishing points. Ah, they're tilted differently, so they're going to have different, there's going to be 3 vanishing points to deal with. There's going to be one that goes off to the right, one that goes off to the left, and what about this one? That's in what kind of perspective to this character? 1 point perspective. And we do the same thing. We want to find the vanishing point for that line, so we'll run a parallel line to those, which means it's going to be right there on the picture plane. That will be a vanishing point line. Where will the vanishing point line be for that line? Make sure it's at a right angle.